In this short little lesson, we are going to review both the disk and shell methods. So first, let's do a disk method problem. So given the graph of secant x between 0 and pi quarters, find the volume of the solid obtained when this region is rotated about the x-axis. So first, notice that pi quarters is just a little bit less than 1. So we're taking this region and we're spinning it about the x-axis. Now think, do you want to slice like this, or would you prefer to slice like that? And I think option 1 is better. Option 2 involves two cases, 1 until you get up to 1 and then 1 past 1, so let's not. So if we slice the first way, so if we slice like this, our volume is an integral from A to B, the area of a slice. And our slice is our R circles, so it's an integral from 0 to pi quarters. Pi, the radius is secant squared dx. So that's pi times the integral from 0 to pi quarters secant squared x. Look, I chose my function carefully. What's the antiderivative of secant squared? Well, it's tangent. And what is tangent of pi quarters? Well, it's 1, and tangent of 0 is 0, so this volume is pi. Now, this question is a question that I gave on an exam to my students last year. So I had them set up, but don't solve an integral for the volume of the region between these two curves rotated around various axes. And in these 4 questions, every single problem can be set up using either the disk or the shell method. So we're going to set them up both ways. So first, graph the curve. So square root of x. So that's the point. Those are the points that root x goes through, and 1/2 x. Okay, so there are our curves. So first, x-axis. So if you do the disk method, so here's what you have to remember. Disk, you slice perpendicular to your axis of rotation. Shell, you slice parallel to it. So for the disk, you're slicing this way. So you're going to have a circle with a hole in it as your cross-section. And the volume will be pi. Integral, your slices begin at 0. They end at x equals 4. Your R out is root x. Your R in is 1/2 x dx. And that's good enough for a setup. If you want to check it, this should be 8 pi thirds. So that's the disk method. If you do the shell method, so 2 pi, in this case we have to slice parallel to the axis of rotation, so like that. And we will have to solve both of these expressions for x. So x will equal y squared for the first one, and x will equal 2y. And so this integral, our slices begin at y equals 0. They end at y equals 2. The radius out to the slice is y. And the height of a slice is going to be 2y minus y squared. And one way that you can know if you're right by setting them up both ways is by setting both integrals up and plugging them into Wolfram. And I got 8 pi thirds for both of these, so I'm pretty certain that those are correct. So that's the rotation about the x-axis. All right, now the y-axis. So same thing. You only have one grid. I'm going to draw the picture again. All right. So about the y-axis, so let's do the disk method first. So for a disk, we slice perpendicular to the axis of rotation. So there we're slicing horizontally. pi r out squared in that case. So we have, once again, x equals y squared and x equals 2y. In that case, r out is 2y. R in is y squared. So pi r out squared minus r in squared. And the bounds there are your slices begin at 0 and they end at 2. And if you're checking, this one should give you 64 pi over 15. Okay, now if we do shells, slice parallel to your axis of rotation. So we're slicing like this. And the formula there is 2 pi. Now our shells begin at an x value of 0 and they end at an x value of 4. The radius will just be x and the height will be root x minus 1/2 x. And as long as you've done everything correctly, this should also give you 64 pi over 15. So disk or shells, either one. And then next we have some funky axes of rotation, so things that are not the x or y axis. So regraph our curves, 0, 1, 1, 4, 2. So there's the root. Here's the 1/2 x. Okay, draw in the y equals 4, so we're up there. Okay, so first let's do the disk method. So perpendicular to the axis of rotation, we're going to slice this way. So here, r out will be 4 minus 1/2 x, and r in will be 4 minus root x. And so our volume is pi integral 0 to 4. 4 minus 1/2 x, the quantity squared, minus 4 minus root x, the quantity squared, dx. And if you work it out, I'm pretty sure you're going to get 8 pi. Now for shells, we're slicing parallel. So just to see a different color, looks like that. So your radius is going to be 4 minus x. That's the part that changes here. Wrong, not 4 minus x, it's going to be 4 minus y. And your height will equal rightmost minus leftmost. So 2y minus y squared. So there the volume is 2 pi integral 0 to 2, 4 minus y times 2y minus y squared dy. And assuming you've done it all right, that should also give you 8 pi. All right, and finally a vertical line. So x equals -3. So that's over here. Okay. So first we'll do the disk method. So slicing perpendicular to the axis of rotation. So those are horizontal slices, hence they're going to be y's. All right, so first of all, r out. Well, to get from here to the y-axis is 3 units, plus that little bit looks like 2y. So r out will be 3 plus 2y. R in will be 3 plus y squared. And so using the disk method, the volume can be found by using pi integral 0 to 2, r out, which is 3 plus 2y squared, minus r in, 3 plus y squared, squared, dy. And if you work that out, it gives you a rather nasty answer, 184 pi over 15. Now using the shell method, so for the shell method, we're slicing parallel to the axis of rotation. So the volume is 2 pi. So our slices begin at an x of 0, they end at an x of 4. And the radius, the distance from here out to your slice, well, that will be 3 and a variable distance of x. So 3 plus x. And the height of a slice, top curve minus bottom curve, so root x minus a half x. And so assuming you've set them both up correctly, there you go, you should get the same answer, both 184 pi over 15. All right, let's do another one. So graph the region bounded by the curves 2x and x squared. And then set up, but don't solve the integral. It gives the volume when you rotate it about the following axes. State the method that you're using. So you have 0, 0, 1, 1, 2, 4. And 0, 0, 2, 2, 2, 4. It's actually pretty much the exact same region we had before. So you pick x-axis, you could do whatever you want. I am just going to choose to use the washer method, although the disk method is actually also, the disk, washer disk, same thing. The shell method is actually also possible. So for the washer method, your R out is 2x, your R in is x squared. So the volume would be given by pi integral 0 to 2, 2x squared minus x squared squared. And simplify it whatever, but that will give your volume. Now, y-axis. So same picture. Now personally, I just want to be lazy and not solve the equations for x, so I am going to use the shell method in this case. Although the other method does work. So 2 pi integral, so our slices are looking like this. So the slices begin at an x value of 0 and they end at an x value of 2. The radius, distance from axis of rotation out to it, is x. And the height is 2x minus x squared. All right. So both of those could have been done either way. In this example, only one way will work easily. So first let's graph the region. So x squared plus 1, parabola up 1, 1 over 1, 1, 2, next point. So there's x squared plus 1. 9 minus x squared, a little off my grid, but can take it. And they appear to intersect when x equals 2. You could verify by plugging 2 in. When you plug 2 in, you get 9 minus 4, which is 5. And plug 2 in, you get 4 plus 1, which is 5. So, now if our axis of rotation is y equals -1, so down here, the question is can you use the disk method? Can you use the shell method? So disk method involves slicing like this. And you think, is that an easy thing that you can do? And the answer is yes, because you already have equations for the heights of these curves. If you were to try to do the shell method, you have to slice like this, which means you have to solve those equations for x, and that's going to be a lot more complicated. It technically will work, but it's definitely not the best way. So here we are going to use the washer method. All right, so in that case, our outer radius, so the distance from the axis of rotation to the outer curve, so to go from the axis of rotation up to the x-axis is a distance of 1. plus the 9 minus x squared. So 1 plus 9 minus x squared, or 10 minus x squared. Our in a similar fashion, is 1 plus x squared plus 1, or 2 plus x squared. And the volume would be found by taking pi, integral from lower bound of x equals -2, upper bound of 2, r out, 10 minus x squared, squared, minus 2 plus x squared, squared. And the function inside your integral is what determines if you can or cannot use symmetry. So in this case, that function inside the integrand, this thing, that thing is even. So you can use symmetry, and you could say this is 2 pi integral 0 to 2 times 10 minus x squared, squared, minus 2 plus x squared, squared. You don't have to do that, but it is good to know that you can, because if you actually had to, say, solve this integral, it would be a lot easier to do this than do the previous one. Okay, now same region, but vertical axis of rotation instead. So x squared plus 1 9 minus x squared, x equals 6. Okay, so you have to ask yourself, would it be easier to slice this way, or would it be easier to slice that way? And I think for the same reasons as the previous example, the second way is easier. So that means that for this one, you are going to use the shell method. So your volume, 2 pi integral. Okay, first you need the radius. So what's the distance from here out to that thing? I think it's 6 minus x. So the total distance from here to here is 6. This is x. 6 minus x. And before you think that won't work for negatives, think if this was, say, -2 or something, you'd have 6 minus -2, which means it actually is a distance of 8 away. That's actually correct. So 6 minus x is right. Then the height is top curve, 9 minus x squared, minus bottom curve, x squared plus 1 dx. And the slices begin at an x of -2. They end at an x of 2. Let's just simplify a little bit. 6 minus x times, well, it'll be 8 minus 2x squared. Now here, in this particular example, the function inside the integrand, that stuff is not even. It's not, so you cannot use symmetry even though this picture has symmetry. So it isn't the picture that matters, it's the resulting integral that you get. Okay, and lastly, let's do something where the cross sections are not square, as in we don't have a solid of revolution. So the base of a solid is the region bounded by the parabolas, y equals x squared, and y equals 2 minus x squared. So there's x squared, goes through 1, 1, and 2, 4. 1, 2, 3, 4. All right, 2 minus x squared starts at 2, also goes through 1, 1, and then kind of heads on down. So that thing is the base, and when I slice the base perpendicular to the x-axis, I get squares. So the area of my cross-section is found by taking whatever the side of that square is and squaring it. And the length of my side is the upper curve minus the lower curve, or 2 minus 2x squared. And for my volume, I just add them all up. I start adding at -1, I stop adding at 1. The thing I'm adding up is 2 minus 2x squared, the quantity squared. So that's twice the integral from 0 to 1, because that function in the integrand is even. 4 minus 8x squared plus 4x to the 4th. So let's just pull that 4 out because it'll make it easier. Make that an 8. And we have the integral from 0 to 1 of 1 minus 2x squared plus x to the 4th dx. So that will be 8 times x minus 2/3 x cubed plus 1/5 x to the 5th. And that's 8 times 1 minus 2/3 plus a 5th. Getting a common denominator, that's 8 times 15/15 minus 10/15 plus 3/15, or 8 times, looks like 8/15, which is 64 over 15.